Well, good morning, everybody. How are we doing today? Pretty good. We've come out of the darkness of yesterday's lab into the light again once more. What do we have to do here? We need to do one kind of massive chapter 27, that covers both interference and diffraction together, right? So your author lumped them all together into one chapter. Should be two, but lumped them into one. We've got to do that today and Thursday, and maybe next Monday, because what's happening next Tuesday, a week from today? Review, right? For the exam that is happening a week from this Thursday. So next week, right? Tuesday is review, Thursday is the exam. Monday is going to be like a catch up. I'm probably not going to be done with chapter 27 in time. And I'll do a little bit more lecture on Monday, and then we'll have opportunity to do like GRASP and help you with their homework and get everything sort of set up. So that's the plan. You are taking your exam the day before Halloween, so I will endeavor to make it extra scary. No, I shouldn't say things like that. And then we have, after that, we have one more exam, and this class is done, right? We're past the halfway mark. What is this, the 10th week? Something like that? So it's the 11th, but who's counting? Right? Oh boy, so much fun. Okay, so why is chapter 27 so big, and why am I not going to get there in time? Chapter 27, interference and diffraction, this was my graduate work. I did interference, thin film optics specifically, so when we get to thin films, I'm really going to kind of bore you with a lot of technical detail. But this was my jam. Right? I love this. I love all of optics, and for me, corrective optics, eyeballs, lenses, glasses, right? I understand that all very, very well, but it's a sideshow compared to with like what I was doing in my undergraduate and graduate research. And interference and diffraction are the basic physics for what I consider to be why nature is beautiful. I mean, if you look at a bird's feathers, right? This is a hummingbird. I can't remember what species this is, right? But hummingbird feathers certain hummingbird species have this iridescence to their plumage, like the color that comes off of their feathers, right, is the result of the physics of what we are going to talk about. Interference and diffraction. These colors don't happen unless there's very thin films of oil on the bird's feathers that help the feather stay waterproof and things like that. That just gives rise to such incredible beauty. So bird's feathers, butterfly wings, how to get coatings on optics that keep reflections from, say, ruining the photograph. Thin films and interference and all of these things have so many applications, and I just love it. I just love this stuff. I love it. So the thing about so we just spent 2 chapters on reflection and refraction, right? We did mirrors. That was the law of reflection, and then we did lenses. That was the law of refraction. Now, these interference and diffraction are the 2 things that only waves can do. So we really got to dig in and think about the wave-like nature of light. We can fake refraction and reflection with particles, but really where this comes down to it, you can only have waves doing the following. And this is a little bit of call it a review, right, from 2A. Talked a little bit about waves and what they do. But let's say we've got a couple of waves that are going along and they're doing this, and we want to add those 2 waves together. Wave superposition means that waves can be at the same place at the same time as another wave. And there's sort of two possibilities. There's an infinite amount of overlap, but two big possibilities for what you can get when waves superimpose themselves or end up at the same place at the same time. I made that second drawing not look so good. All right, but you get the idea, right? Okay, so what happens if we add together these two top waves? Like we try to put them at the same place at the same time. What does that sort of drawing look like? What happens when, like, do you remember like what happens when a peak and a peak kind of overlap? Yeah, they build on each other, right? So what you do is you literally add like every point to every point. Like 0 plus 0 is still 0, but whatever this amplitude is, and this is the same amplitude, you get twice the amplitude, and you get 0 and 0, and then you get twice the opposite amplitude, right? So you go through, and what you end up with is a wave, right, that ends up with double amplitude, right? And this is called constructive interference, right? In the sense, interference is superposition, okay? It's waves overlapping, and we're trying to figure out what's going on. And it's kind of funny to use the word interference because I think Americans go straight to like pass interference in football, right? Like you've gotten in the way. We're not talking about getting in the way. We're talking about literally like overlapping in space and time, okay? And so constructive interference means that overlap builds, right? It makes the outcome bigger or stronger, more intense. And then what happens if we have two waves that are overlapping that are opposites of each other? Like this one's up and this one's down at the same place, so what's going to happen? It's going to cancel it out, isn't it? It's just like, right? And this one's up, but this one's down, and these are all zeros. And what you end up with here, right, is a flat line. Okay? there's just nothing, right? There's just it completely cancels out. And to no one's surprise, we call this destructive interference. Now, here's a glossary for you of terms that are all used. All these words are trying to convey the same thing, right? So we'll refer to constructive interference sometimes as like the brightening of a wave, like especially with light, okay? We'll say the amplitude increases. All of these are ways of sort of describing constructive interference. Destructive interference, we would mention how maybe there's an absence of light or darkness, or like the waves diminish, right? Like those are all ways to try to describe destructive interference. In physics, we stick to constructive and destructive interference, but then we also throw around some other terms that are actually very precise in their usage, but at first can seem a little bit, wiggly. We'll talk about the phase relationship between these two waves. The two red ones, the ones at the top that are making constructive interference, we say that those waves are in phase. And by that, we mean they're wiggling the same. In other words, when one is peaking, the other is peaking. When the other one's troughing, the second one. Is troughing a word? Yeah. I just made it up. I said it, so therefore it is, right? Okay, so the rule of today's internet, right? If I post it online, it must be true. Okay, so if the two red waves up there are completely in phase with each other, okay, then what's the words I could use to describe the two blue ones? Out of phase, right? Okay, so you have in phase and out of phase, where phase specifically in wave mechanics refers to a shift of a wave. So the two waves up there are in phase, And another way to talk about their phase relationship is that they are 0 degrees offset from each other. Now this is going to get a little bit more weird because now we're getting into some trigonometry things, okay? In trig, I don't want to belabor this point, and I don't want to torture you with having to remember anything from, say, high school or the beginning of college, but there was a relationship where if you had, what was it, sine of any angle plus or minus 90 degrees. Does anybody remember what that's equal to? Like if you shift sine or cosine 90 degrees, what do you get? You get the other one. Okay? That's because, like, if we take a sine wave that looks like that, right? And then we shift it, let's say we just shift it to the left 90 degrees, right? And I'm going to cheat a little bit because I'm using the board here in the front, right? Okay? But I can cheat, and I can shift this over by just changing the origin of coordinates, right? And now, what is this wave right here? That's a cosine, okay? So in wave theory, and particularly in optics, we will talk about the phase shift of different waves. The phase shift of the red ones is 0 degrees, okay? And again, we're referring to, right, a difference in their wiggles, okay? You want to guess how many degrees the blue ones are? It's 180, right? It's like exactly opposite. Excellent, okay? So this phase angles are usually phees, okay? This would be 180 degrees, okay? So again, I'm just trying to arm you with some terminology, some glossary, right? I might get really excited and start, instead of saying constructive interference, I'll say the phase angle is 0 or 360 degrees. Well, 0 and 360, how could that be the same? If I were to shift this wave 360 degrees along, I would get back to exactly the same wiggle, wouldn't I? Right? It's because it just, a cosine or a sine function completes itself all the way around the unit circle. So I apologize in advance, right? But this is standard terminology in textbooks, online, wherever you go. The phase relationship between waves determines whether or not it's constructive or destructive interference. We will limit our relationships to these two extremes. There are in-betweenies, right? You can get phase relationships of any angle. But we're gonna limit ourselves to either 0/360 or 180. Okay? Now, why does all this matter? Well, let's go back to Thomas Young. Who was Thomas Young and what did he do? Stood up against Newton. How did he do it? He did an experiment. Does anybody remember the name of the experiment? It was the double slit experiment. Okay? So what we're going to do is we're going to get into this experiment in detail. Right? The detail that I want you to concentrate on or focus on isn't the actual equations that we're going to use. We're gonna dump some equations out, and you just put them on your cheat sheet and plug and chug your way through the problem. That's not the important part. Okay, the important part here is the overall method and approach, because we're going to use double slit interference as an example of how we are going to tackle thin film interference, which is definitely the harder of the two. The double slit experiment that Thomas Young did has no practical application. I don't have a picture of it. It has no practical application because by that I mean, right, in nature, are you ever going to see two very narrow slits right next to each other with monochromatic light shining on it? The answer is no, right? And like even in instrumentation, except for very specific situations, double slit interference is not useful to like do anything with. It's a great proof of the wave-like nature of light, but it actually doesn't have any application that is useful beyond certain measurement regimes and all that kind of stuff, okay? So what's going on in the double slit? Light hits two very narrow, and by narrow we say like really small compared to the wavelength. Now, visible light has a wavelength of anywhere from 400 to 700 nanometers. And so what we need these slits to be is super duper small compared to that. We need like 100 nanometers, 50 nanometers. They need to be really tiny, and they need to be offset from each other a little bit, okay? So they'll hit these slits, and then the waves will bend out from these slits, okay? And wherever the waves overlap, because I didn't draw this very well, okay, they will either constructively or destructively interfere. And this is kind of what I was trying to give you in that glossary right here, okay? So the fact that light is coming out of two different slits, two different sources of light simultaneously, okay, means that one wave is going to travel a certain distance to get to the screen over here, right? Like this one's going to travel there, this one's going to travel that way, okay? And they're coming in at slightly different angles and slightly different distances, okay? And the question is, well, what happens when they come together? Wherever it is they're coming together, what's going to take place? If I have a wave, right, where one's going up at the same time the other one's going down, it's called destructive, right? And if we can get the situation to happen such that when they come together, they're both peaking at the same time, that would be what? Constructive interference. Okay, so let me show you what this looks like when, okay, so Thomas Young didn't have lasers, okay? If he had I've often wondered what would happen if like ancient historians had like cell phones, right? And old physicists had lasers. Like, can you imagine like pick famous historian and give them a cell phone to be able to like record, right? What happened at Pompeii? Pixar, it didn't happen, right? Okay, so if Thomas Young had had a laser, he could have pulled this off much easier, and the world wouldn't have guessed so much. He didn't have a laser, so he got very clever about how he collected sunlight. He had sunlight sort of illuminating this. He brought the sunlight in with a series of mirrors, and it illuminated this box, and then from that box he used clever optics to make sure the light was all, we call it collimated, it was all coming very nice and evenly and flat, and then it hit these two things. He had to deal with all the colors of the rainbow, which is difficult. Lasers are nice because they are they are single color. We say that they are monochromatic. We'll get to lasers and how they work later when we get to quantum mechanics. But this is what double slit interference looks like. Maybe. And of course we don't have any sound, so I will narrate. They're just showing you how they can move the laser onto differently spaced slits that are on that card right there, right? They can adjust where the laser hits which slit, and the slits have different like widths and spacing between them. But notice there's a lot of distance, right? And the slits are very narrow, okay? So there we got a slit spacing. The distance between the slits is at the top of the screen. As we make the distance between the slits smaller, the pattern spreads out, okay? But we're seeing a bright dot and then like a dark area and then another bright dot and a dark area and a bright dot and a dark area. So that's the experiment that started the revolution, right? And the story with Poisson and all that kind of stuff, right? And it's like, that was dumb. It's just, it looks like Knight Rider, that's it, right? So what's the big deal? What does constructive interference look like for light? If two light waves are getting together, what's that light going to look like on a screen? Doubled, bright. And what will destructive interference look like on a screen? The absence of light. And so in this pattern here, we have bright spots. Those are spots where the light's getting together and constructively interfering. And then next to it, there's a dark, we usually call them fringes, like a dark fringe. There's a light fringe and a dark fringe. There's a light spot and a dark spot. I know fringe has a different connotation depending on what context you're using it in, but nevertheless, that's terminology that's used to describe what's going on here. But we've got bright and dark, bright and dark, bright and dark, constructive, destructive, constructive, destructive, constructive, destructive, all across the screen. If we sort of zoom in on these fringes, right, the bright ones here would be the constructive situation, and the dark. And this pattern, this interference pattern that exists, is like a dead giveaway to the wave-like nature of light. What we're about to do cannot be described if we're doing particle physics. Okay? We have to use wave physics in order to get it to work. I know that this screen looks really scary because there's a lot of angles and labels and things. Again, when we get down to the equations, it'll be the ones you write down. It's the ones you'll need for your homework. But the reason I'm taking you through double slit interference is to give you an overall sense of how we approach these interference problems. Okay? So let's not get too deep into the details here, right? But let's see the overall approach. And this overall approach is going to help you a lot when we get to thin film interference. Okay? So it's really this middle picture that we should be concentrating on. These two wiggly lines right here mean that there's just a lot of space, right? We're just not going to draw the full scale diagram of this. In that experiment, the slits were hundredths of a millimeter apart from each other, right? But the screen was like 3.5 meters away, right? So there's a huge difference in like how far away you need to project this thing versus how small your slits need to be. And so that's what these kind of wiggly lines are doing right here. But in the end, what's going on? We have one slit that's sending a ray of light towards the screen. Again, this is a wave, but we don't draw the wave. We just draw the ray that shows us the direction of propagation. Okay? And we have another one that's on its way to the screen. Okay? We want them to hit at the same place. But the two rays are not traveling the same distance to get there. Which of these two, top or bottom, goes further to get to the screen?
Where's the screen?
Can you see it? Well, the screen would be like over here somewhere. Maybe if I'll draw it over here, okay? I'll draw it right here. We'll do our own version, right? So we'll do a double slit like that. We'll do a screen over here, right? And we'll say that this ray is coming along and it strikes a point on the screen right there. We'll call that point P. And then we've got another ray that comes from the bottom, comes up, and also strikes point P. Oh. Which of those two distances is bigger? It's the bottom one, isn't it? Okay. And if we like mirrored this, so there's like an optical axis that goes along right here, right? And this is like the zero, the origin, right? And if we mirrored this point down here, right, same distance down, then it would be the top one that goes further, right? So it doesn't. So that's why you'll see pictures, okay, of these. See, notice how in this picture they're giving us 0, which is the very center of the slits and the screen and all that kind of stuff. And then they're just using counting numbers going up and the same counting numbers going down, right? It's because there's a mirror across a mirror effect. It's not literally a mirror. In optics, I got to be careful, right? But the effect is above and then mirrored below the optical axis. Okay, so the question comes down to how much further does the bottom one go? And we refer to the distance a wave travels in an optical system, we call that the path length. So if I know the distance between two lenses, right, in an optical system, then the path length that the wave travels between the lenses is the distance between the lenses. The path length for the rays I've drawn on the screen, right, would be the distance from where they come out of a slit to where they hit the screen, whatever that distance is. And it's not the actual path length that matters in interference. This applies to double slit, thin film, any kind of interference. It's path length difference. It's the extra distance that one ray has to travel compared to the other. And that path length difference can be found right there. I don't want to get into the nitty-gritties of how you derive all of these things and the geometries and the cheats that we do in terms of small angle approximation. There's a lot of physics and mathematics and arguments that go into how we do this. But kind of a simple way to visualize what's going on here, right, is to drop that sort of blue line down that makes a 90-degree angle, and then we have this extra distance right here. This is called the path length difference, PLD. Okay? That's the extra amount that the wave is going. If we know the distance between the slits, and we're familiar with how angles work getting to the screen, okay, we can actually find out what this path length difference is. And that's what this picture right here is trying to kind of show you, right? They're using the symbol delta L for path length difference. I've only ever seen that in your book, okay? So what does this all boil down to, okay? In interference, the thing that you want to do is you want to set your path length difference equal to some condition, okay? The path length difference can be found, and I'm just going to tell you, for double slit interference, the path length difference is d sine theta, where d is the distance between the slits. It's not how big the slits are. It's not, how wide those slits are, but it's the separation between the two slits. We'll talk about the angles here in a second. We'll get back to that, okay? But trust me, the path length difference is d sine theta, okay? What's the condition? The condition is what we want to have happen at some point on the screen. And there's two choices. What are the two choices for what can be happening on the screen? The waves are either constructive at a point or destructive at a point. For us, there can be in-betweenies, but we're just going to do the two extremes, okay? And in this black and white picture here, you see that we're labeling things. The negative signs don't mean anything here, okay? The negative signs literally are just trying to say you're on the other side of zero, okay? But the fact of the matter is that the pattern repeats itself. Whatever the pattern is going up, it's the same pattern going down. Where we call zero, we call that the central maximum. At the point where two rays, starting at these slits, would travel exactly the same distance to the screen, the path length difference would be zero. They travel exactly the same distance, so there is no path length difference. So whatever the waves are doing, If they're coming through those slits and peaking, right, or troughing or whatever, the two waves are going to be totally in sync with each other. The problem is what happens when this path length difference causes waves to shift with respect to each other. The path length difference can be a multiple of the wavelength. And so if the path length difference, the extra distance that a wave has to travel, is equal to a complete phase of the wave, then we haven't changed. If it comes out peaking, it'll get there peaking. Okay? But if the path length difference is any different from the actual phase length of the wave, all kinds of stuff can happen. What do I mean by that? So the condition can be constructive or destructive. And weirdly, we're going to refer to this constructive and destructive things in terms of the wavelength of the light. I just got finished telling you about phase changes and all that kind of stuff. They'll come back later. But the condition is a multiple of the wavelength. This equation right here will give you constructive interference. Let's read what it's trying to tell us. The overall idea here is the path length difference, the extra distance one wave is traveling compared to the other. If that distance is equal to, say, one wavelength, so the two waves come out peaking, but one has to travel an extra distance, and that extra distance is exactly equal to a wavelength, you will get the two waves arriving on the screen totally in phase, constructive interference. However, if the path length difference, notice the path length difference doesn't change. It can be a number that's different, but the equation for the path length difference stays exactly the same because that's set by geometry. If the extra distance that one wave has to travel compared to the other turns out to be a half of a wavelength, and the way we write half of a wavelength is like this, okay, then this is destructive interference. Why did I write it with m's and halves and all that kind of stuff? So let's go back to constructive. Does it matter if the path length difference is one wavelength, two wavelengths, three wavelengths, or 100 wavelengths different? When you go through a complete wave, doesn't matter if you go through 1 or 10 complete waves, what are you going to end up doing? You're going to be right back to where you start, right? It's going to be exactly the same thing. So that m value is a counting number. It's always an integer. Okay? In the case of m lambda, you got to start at 1 because 0 times lambda doesn't mean anything. So you start at 1, but it doesn't matter if the path length difference is equal to one wavelength, two wavelengths, three wavelengths. All of those will give constructive interference. And so we write the other one, m plus a half, to indicate it's any half wavelength shift. So it could be just a half, right? We could put m equals 0 into that right there for the destructive case, and we'd have a half wavelength. But what if we put in m equals 1? Well, then we've got 3 halves, right? M equals 2. 5 halves, right? Like it's multiples of a half wavelength that will give you the destructive case, where one wave is offset by a half wavelength from another. D, it's the separation between the slits. It's coming. It's just the Wi-Fi wants to be slow. Okay? So that separation right there, that distance between them. Okay? And then technically there's an angle. I always hate having to draw this one. Okay? There's an angle that is referenced, okay, to where you are on the screen.
And that'll always be midway through D? Or that varies?
I'm going to lie to you and say yes. Okay? It's a lie because technically the angle should be the angle that that ray makes and the angle that that ray makes. Okay? Do those two angles look different to you? They should, because they are different, aren't they? Here's the problem. On the screen, I can't possibly draw it correctly or to scale. So let's say, can anybody see that double slit? Yeah, it's really tiny, right? Okay? And the screen is somewhere over here, right? This would be the true scale of the problem, right? So, I really don't want to do this because I don't want to have to erase it. Okay? But if I start drawing a line from the top slit all the way over to the screen, and then I come back and I draw another line from the bottom slit to the screen, can you tell the difference between the angle now? Barely. No, you can't. It's so small that in the end it turns out to not matter. Okay? So that's called something called the small angle approximation, and you really don't have to worry about it. You don't have to worry about it to the point where if we say that L, capital L, is the distance. I can't remember what your book uses. Your book writes these weird. I always hate the way your book writes it. Your book writes it as sine theta equals m lambda divided by d. I've never seen anybody in optics write it like that. It's d sine theta equals m lambda. Like literally, like you just, why are you doing fractions when you don't have to? So just deal with it, I guess. But there is, it's not a cheat. It's a mathematical way of doing things, or in other words, a cheat, where because these angles are so tiny, sine of the angle and tangent of the angle are about the same number. And since tangent is equal to the distance y, the vertical distance from the center to where the point on the screen, tangent would be y over L in that, it's opposite divided by adjacent side. But this down here is called the small angle approximation, which is why sometimes you'll see this written as dy over L equals whatever condition that you're trying to get to. M lambda or m plus a half lambda. So you'll see that this is the one that I use whenever they ask me to calculate the angle. I'm like, no, the angle is y over L, right? It's just, try it in your calculator sometime. Put your calculator in radians mode and do sine of 0.01 radians. It'll be equal to 0.01. The angle, the tangent of the angle, I should put theta, sine, tangent. When the angles are so tiny like they are in this situation, the sine doesn't matter anymore. The tangent doesn't matter anymore. You can just write them all down as equivalent things. All right. But that, see, I was going into details I didn't have to go into. What matters? What matters is what's in the box. Okay, those are the equations that you'll have to deal with when it comes to two-slit interference. The major thing that matters is really this idea up here. Because what we're about to do, after I do an example of doing double slit calculations, we are going to move into thin films. And in thin film interference, it's path length difference equals condition that is going to enable us to be able to figure out why hummingbird wings look the way they do, why $20 bills have a security feature that you can use at any time, and why we can figure out how much oil has been spilled by a tank. There's so many applications of thin film interference, okay, right? But they all begin and basically end with path length difference equals condition. If we understand that idea, you can solve any interference problem. Okay, so let me also point out here, okay, again, this sort of numbering, right? So this only applies to two-slit interference. If you're talking about an integer value, you automatically know it's constructive. That's why all of these bright fringes have been labeled with an integer number, okay? Why have they labeled the dark ones with half integers? Yeah, destructive is all about getting a half wavelength off from something. 180 degrees phase difference and half of a wavelength are the same thing. They're just different ways of describing what's going on there. Okay, so let's do an example, okay, of just solving a two-slit interference. This is what Thomas Young was doing, right? And the only way that you can work this problem out is by assuming light is a wave, it has wavelength, because only waves can have conditions like constructive and destructive interference. So, what do we got? All right, light has a wavelength, 546 nanometers. I'm going to write that down somewhere. Lambda, 546. Okay. Okay, so there's like some geometry here, right? They tell me that the screen is 8.75 meters away. So what I kind of picture in my head, right, is a couple of double slits, a screen, and the distance is 8.75 meters, right? Okay. The linear distance on the screen from the central fringe to the first bright fringe. So what we've got here, right, is this 0, okay, not degrees, 0 right there in the middle, the central maximum, right? And then they're saying there's a distance to the next bright fringe. That distance is 5.16 centimeters, okay? So that's what they've given me. They want to know the separation of the slits. So, what do we use? What do we got? We've got d sine theta equals m lambda, and we have d sine theta equals m plus a half lambda. Which one of these equations are we going to use to figure out d? Think about what they've told us. We're going from the central, everything's measured from the center, to what? First bright. So what's brightness? What's a bright fringe? It's constructive, isn't it? Which of these equations is all about constructive interference? M lambda, right? That's the one. So we're not going to use the destructive. Now, if the problem had said to the first dark fringe, well, then you would have had to use the destructive case, right? But we are talking about bright to bright, so that's what we're going to use. All right. So we're going to use d sine theta equals m lambda, and I don't know about you, but I really don't want to go find this angle. I mean, I could. I've got L and I've got Y, don't I? So I can find the tangent of the angle, use the inverse tangent, put that into sine. But I already just told you that there's an alternative way to write this equation because of math. Right? Y over L can be substituted in for sine theta, and you can avoid trig altogether. This is just called the small angle approximation. Physicists and engineers the world around depend on this. When you've got a small angle, guess what you don't have to do? Sine or tangent. It's y over L when we're done, okay? All right, so we're going to use this d sine theta just becomes dy over L. This is unique to small angles and double slit interference. All right, so what are we solving for? We're solving for d, right? Well, I can do algebra, maybe. How'd I do? Divide both sides by y. multiply both sides by L, right? Okay, so there we go. Okay, so I know L, I know lambda, and I know Y. What the heck is M? What's the M supposed to be doing in all this stuff? It's just counting, right? Is there anything in the problem that sort of clues us in to where we are on the screen? First, the first bright fringe. And so we go back to this picture right here, and the first bright fringe next to the 0th is M equals 1. Or negative. Don't worry about the negative, right? It's 1. So I'm going to go ahead and I'm going to say, okay, 8.75 meters times 1 times what? I'm giving you the old man skeptical, you better get this answer right. 546 times 10 to the minus 9 meters. Why? Because I've already got something in meters. And I better have, right? Okay. So 546 times 10 to the minus 9 meters. Okay. By the way, that M right there was meters. I don't know. Too many M's flying around in this stuff, right? Times 1 to that. And then the Y, what am I going to write down? 5 point. I'm going to do 5.16 times 10 to the minus 2 to make sure I get it into meters, right? Or 0.0516 meter. What do I have to be careful to do? I got to get my units right. If I take a meter and I divide by a centimeter, I have no idea what's going on. That sounds like English, okay? It doesn't sound like math or physics. So be careful with your units. This one had meters, centimeters, and nanometers in it, right? Warning, very quickly and very soon, I'm going to start leaving the wavelength in nanometers in the problem, okay? If I leave the wavelength in nanometers, but the L and the Y I make sure are the same unit, both meters, what happens if you have a meter on top and a meter on bottom? They cancel out, and if I left my lambda as nanometers, I would get nanometers back out, right? In optics, especially thin films, we tend to leave the wavelengths in whatever wavelength, whatever unit they've given us, because as long as we're careful with all of our other distances in the problem, make those the same units, then our answer is going to turn out in the same units as the wavelength, which is actually quite handy when you're trying to design optical systems. So the safe thing to do is convert them all into meters, because you're guaranteed to have what come out? Meters, right? And then you'll have to convert back if Wiley Plus is being annoying about, well, what is it in picometers? Right? Wiley Plus, right? Oh, by the way, Canvas apparently is back. I'm not sure if I should apologize for that or what, but like, so are any of your other teachers like being super mean? Like, it's not my fault, it's your fault. No? Teachers are being understanding about the outage? I did hear some horror stories of things across the nation. Teachers saying, well, your homework was still due. I don't care that you can't access it. That's your problem, not mine, right? Yeah, I'm not that kind of teacher. So. All right, let's see here. So we did it. No, we didn't get the actual answer. Apparently I don't care. Double slit, lambda. Is this 92.5 times 10 to the minus 6? That's what it looks like. Yeah. 6 times 10 to the minus 6 meters. So, or 93 microns. All right, so that's a number, right? And numbers bore me. So, all Let's move on. Let's move on to the main event. Okay. I spent 4 years of my school career as an undergrad and graduate student doing nothing but this. Okay. And though that was, oh my gosh, 24 years ago now, I still consider myself to be an expert in thin films. I would probably need a month or two to really get back up to speed with all of the mathematics and stuff that I would need to be able to model certain things. But like, my expertise and training is in thin films, right? I consider my current expertise to be in how do people 18 to whatever years old learn physics, right? That, like, my expertise is physics teaching and physics learning. But my second expertise and my second love in physics is this. So I apologize, because you're going to get way more detail than you need. But, you know, teachers do this, right? They're like the one thing they either specialize in or really excited about, and they go into way too much detail, and you guys are just drowning. I'm going to be, I've already thrown you in the pool, and now I'm just going to push you down and hold you under. Okay? Now, all that being said, I do need to warn you that thin film interference is hard. It's hard in the same sense that Newton's second law in physics 2a was difficult. In order to solve a thin film interference problem, you have to derive the equations for every single problem. I'm about to lay down d sine theta equals m lambda and d sine theta lambda. I'm going to lay down exactly the same equations. However, the equation's meaning is going to change for every single problem, because the equations will be applied differently depending on what's going on in the problem. And I think that makes it difficult, because what you want is, Mr. Balogh, this is the destructive equation. This is the constructive equation. It never changes, right? No, it changes every single time. And so the actual equations themselves are not difficult. The actual doing the math is not difficult. There's no small angle approximation in this one, so we'll actually be using these things. But like, the concept, and I know you guys hate that word, but the concept reigns supreme here. Don't give up and just throw your hands up and say, you know what, I got a 50-50 chance, right? You'll be sitting there on the homework, right? And you'll be working it, and you'll get it wrong, and you'll just choose the other one, and you'll get it right, and your brain will want to go, oh, I finally got it, I'm going to move on with your life. Don't let that happen. You have to stop and figure out why you got it wrong the first time, okay? If you're in ChatGPT and ChatGPT is doing your homework for you, don't just passively go, oh, it picked m lambda, fine. No, you got to know why it picked that, okay? Especially because it could be wrong. So, like, watch out. Okay. What is thin film interference? It's bubbles. Bubbles is one example. And I love bubbles. I've loved bubbles since I was a kid, right? But like, I especially love bubbles now, okay? Why? What's so amazing about bubbles? They float, they fly. I can make them myself if I have a bubble wand and some bubble juice, right? But as they move through the air, right, the incredible colors, right, that are generated by that very thin, very tenuous layer of soap and water, right? Okay? Air on the inside, air on the outside, but in that very, very thin interface, an incredible amount of optical physics is taking place to bring us all of these colors, right? This right here, okay? This is oil on water. If you walk through a parking lot in a rainstorm, especially if it hasn't rained for a while, you'll see little rainbow patterns on the surface of the water in the parking lot where gasoline and oil and coolant and whatever else leaks out of cars, right, collects. And then the water comes in and starts lifting those materials out. And you get these very thin films of oil and whatever on the surface of the water. And it will cause these kinds of patterns to exist. It's because there is a thin layer of material, right, riding on the surface of something. And it's a type of sandwich. There's air, and then there's this very thin layer of material, and then there's something else that thin layer is sitting on. We call it the substrate, okay? Whatever material is holding up that thin layer. In the case of a soap bubble, it's air. That would be the substrate, okay? The incident material, the material that the light is traveling in before it gets to the thin film, right? Again, varies depending on the application. Most of the time it's air, but you can have situations where light's traveling in glass and then it hits plastic before it hits air. If we want to get super technical, it's called the superstrate. So you have the substrate, the material on the bottom, you have the superstrate, the material on top, and then you have the thin material that's kind of sandwiched between them, okay? So, more soap bubbles. Oh, this picture. So camera lenses, whether it's your phone's lens or an actual, like, real camera lens. Not that cell phone cameras aren't real. Anyway, I consider them not real because I was trained as a photographer. Do you see the purple sort of haze on this lens right here? That purple light is coming from a very thin layer, I believe, of magnesium fluoride that sits on the surface of this lens. That thin layer is an anti-reflective coating, okay? AR coating. If you wear glasses, you will probably given the option when you ordered your glasses to have like an anti-reflective coating put on them. What does an anti-reflective coating do? Stops or lowers reflections. In a camera, this is really important because you want to avoid something called lens flare, unless you want to digitally add it back in later in Photoshop, which I don't understand. Lens flare is a defect, okay? And, J.J. Abrams needs to be shot. No, I can't promote violence again. J.J. Abrams needs to be fired for what he did in half of his movies, especially Star Trek, right? Where there always seemed to be like a lens flare coming from somewhere, right? It's an optical problem. If there's a lens flare happening, there's an optical problem, okay? And they did it on purpose by shining bright lights into the cameras. Anyway, supposedly it's art. Anti-reflective coating. I remember the first time I got up to teach in a college classroom, my first class, right? And again, I am a nerd, and back in the day I didn't have laser eyes, and my full nerdiness was on display because I had glasses, right? I showed you my glasses, right? And I remember being really like depressed, down, like nobody in the classroom. And there was 300 of you in this classroom, okay? So I was teaching at a big university, and everybody was being treated like a piece of meat, right? Students were numbers, not names, all that kind of stuff, right? And I was sitting on this big stage. It was like a theater, right? And I was lecturing on physical science. And I remember the students weren't looking at me, right? I was doing everything in my power to be interesting, funny, whatever, right? But my students weren't really looking. They would look at the screen, they look at the chalkboard, they look at everything except me. And I understand, I'm not the most important person in the room. That's okay. But like, I was trying to make eye contact with people. It's like one of the things in communication, you make eye contact, right? Okay? And as I would make eye contact, people would look away. And I was like, Is it me? Like, what's, right? I couldn't figure it out for like 1 or 2 weeks. And so finally I got up the courage one day during a lecture. I stopped the lecture. I said, why aren't you guys paying attention? And everybody was like, what are you talking about? We're taking notes. We're paying attention. It's like, but every time I look at you, you don't look back. You look away. And they were confused. They were shocked. They're like, we're looking at you, Mr. Balogh. You're kind of funny, right? And I was like, but nobody makes eye contact with me. They're scared. Right? And I was asking, are you scared? Is it something I said, did, whatever, right? They're like, what are you talking about? They were like legit confused, right? When finally one student about 3 rows back put his hands in the air and he said, Mr. Balogh, I think I know what the problem is. I was like, what? He's like, we can't see your eyes. I was like, huh? And he's like, your glasses are reflecting all the lights in the room, and so when you look at us, we can't see your eyes, right? Like we're just seeing bright lights where your eyes are, right? And nobody wants to look at bright lights. I was like, oh my gosh. And so I took my glasses off. I couldn't see a thing, and I kept having to ask like the people in the front row, are you looking at me? Like I couldn't, because I couldn't see them, right? Okay. And they're like, yeah, no, we can see your eyes now. We can see where your eyes are going. We can follow your, right? I was like, this is amazing. And so the next time I got glasses, I asked for the anti-reflective coating, and instantly my students started looking at me. Like that. It was just this weird, like psychological thing. Like, have you ever felt slightly uncomfortable talking to somebody in sunglasses? Right? Okay? Because you kind of don't know where they're looking, or even if they're looking at you or anything like that. There's just this subconscious part of you can't make eye contact with the individual. And I'm not talking about like social awkwardness and not wanting to make eye contact. I'm just talking about if you can't see the full part of the human face, there's something wrong, right? Anti-reflective coatings on glasses help other people see the eyes of the person that they're talking to. Highly recommend. Okay. Anyway, it's all brought to you by Thin Films. Okay. So there's a lot going on here, and I'm not possibly going to make it until 9:15. There's no way I can finish this by 9:15. So this is going to carry over into Thursday and maybe even into Monday. This is going to be bad. Okay. What the heck is going on? The physics of what light does when it hits a surface are really, really important for thin film interference. We're going to have multiple surfaces on which light is going to be reflecting and refracting in this situation. But key to understanding what's going on is this idea of what happens when a wave bounces off of a surface. When a wave refracts, nothing happens. The wavelength doesn't shift, nothing happens, okay? Well, that's not true. The wavelength does change. But like the phase of the wave doesn't change. In other words, if a wave was peaking and it goes into material as it was peaking, it stays peaking, okay? Or troughing. The phase never shifts for refraction, but it does for reflection. And there's some rules about this. Back in Physics 2A, and tell me if I have to go yell at Dr. Kerfoot or Mr. Evans, right? Okay. But they should have taught you an idea about wave reflection, where if a wave, like say traveling on a string or a sound wave or anything like that, encounters a rigid like wall, then the reflected ray will come back inverted or 180 degrees out of phase. Does this sound vaguely familiar? Some of you? Yeah, okay, maybe. They should have taught it. They're good physicists. They know to teach this stuff, okay? What does that have to do with light? Well, it has everything to do with index of refraction. If a wave is traveling in a low index material and encounters a higher index material, then in that reflection, the wave will invert itself. The reflected ray will come out upside down from the way it went in. And we say that it has a 180 degree phase change. It shifted from peaking to troughing in the reflection. So that's one rule that we have to just like internalize, right, and be good with, okay? If a wave encounters a non-rigid boundary or a boundary where the wave is free to wiggle, then the reflection will be in phase. If it went in as a peak, it'll come out as a peak. If it went in as a trough, it'll come out as a trough. There's no shift. Speaking in terms of light and how it interacts with materials and matter, if light is traveling in a higher index material and it encounters a lower index of material, the reflection will be no phase change. So what are the rules here, right? If we go from low to high, what happens? It flips. It gets a 180 degree phase change, okay? But if it goes from high to low, nothing happens. We maintain, we say 0 degree phase change. Okay, why is this important? This is the picture that we are going to draw over and over and over again. You will want to draw this picture for every problem that you do when it comes to thin film interference. This picture consists of 3 parts. The superstrate, or what the light was traveling in. The thin film. How do you know which material is the thin one? The problem will state something. It'll say a thin layer. The thickness is small. There'll be some language somewhere that's trying to indicate to you which of the material, of the 3 materials that are in the problem, superstrate, thin film, substrate, right? Hopefully you will get index of refraction for all 3 of those materials, because you're going to have to know something about the index of refraction to be able to figure out what's going on. But what we're going to do is we're going to keep track, okay, of the light as it bounces off the top of the thin film. And we're going to keep track of the light as it refracts into the film and bounces off the bottom interface. So there's a top interface between the superstrate and the film. There's a bottom interface between the film and the substrate. We're going to keep track of both of those things. I can see a little bit of panic in your eyes, especially since I'm not wearing glasses. We are not going to do refraction. We are not going to do reflection, like all of this stuff that we've learned before. We're going to be able to boil this down, okay, to a very concise set of equations that don't require a lot of steps or anything, but does require a lot of conceptual understanding of why it's happening the way it's happening. So don't panic about any of that. But what's sort of the terminology here? Notice T has reared its ugly head. This is not time. This is the thickness of the film. Okay? However thick your thin film is, it's T. Okay? In this example, we're going from air. And air, you're typically not told the index of refraction of air because we always assume air is 1. Right? Air, vacuum is always 1. Okay? But then you need to be told something about the thin film. Let's say this is glass. Okay? With an index of 1.52. Okay? So it goes from air with an index of 1 into glass with 1.52. So what happens to the bounce? It changes phase. By how much? 180 degrees. Okay? But now that it's in glass and it's going back to air, which is 1, what happens to this bounce? It doesn't change, right? Remember, higher to lower means no change. But lower to higher is 180 degrees of change. That's the physics we have to live by in order to figure out what the heck is going on with these 2 rays right here. Our goal is to figure out the phase relationship between the two reflected rays. Because if we made no changes to this relationship, if this first ray is 180 degrees different from the second one, and we try to add them together, what are we going to get? Constructive or destructive? This is destructive, right? They're 180 degrees out of phase, right? So what we're trying to do is figure out the phase relationship so we can apply the correct mathematical statement for what's going on. I'm just going to get a blank sheet of paper here because we got to talk about some stuff, okay? You'll notice in this last picture that the light was drawn coming in at an angle, okay? Technically, there'd be like an angle here, an angle, right? All these angles all over the place. We, as a way of simplifying your life, and be grateful for this simplification, all of our thin film interference that we're going to do is going to involve a ray that is incident normally to the surface, coming straight in, straight down, 0 degrees, okay? So it's going to reflect back upwards. So it came in down, it's going to reflect back upwards. It's going to go in, there will be no angle of refraction, but it will come to the bottom, traveling that way, but bounce off the bottom and come back up. Does anybody see a problem? Are you able to tell the difference between any of the rays that I just drew? No. Why not? Because they're all lying on top of each other. So that's like the problem we're actually going to solve, but we're not going to draw it this way because drawing it this way doesn't let us see everything that's going on. So this is the drawing that I used all the time, even when I was doing the really like hairy ones where there's angles and refraction, all kinds of stuff going on, okay? Ultimately, we ended up coding all of this stuff into computers and making them solve it for us. But we had to be able to teach the computer what to do. Maybe nowadays, if we had ChatGPT, I could have done my master's degree in like 3 weeks. Anyway, I certainly could have gotten it to code for me. What you're going to do is you're going to draw a line that comes in, doesn't matter what the angle is, and it's going to bounce off. And then for simplicity's sake, you will just continue that drawing and bounce it off the bottom. Notice here, I'm not caring about refraction angles. I'm not trying to be specific and to scale or any of that kind of stuff. In fact, a lot of times when I'm going fast, I'll draw this. Right? I'll just do it like that. Okay? What matters here is that I am capturing an idea. That there is a reflection that happens off the top of the film and a reflection that happens off the bottom of the film. And I need to be able to tell I need to know what the phase relationship is for these two. Let's do a couple of examples. Let's say that we go from air to water to glass. And then let's do air to water to air. Okay? What happens at this first bounce? Like, what's the rule? If we're going from 1 to 1.33, what happens at the first bounce? A phase change. We're going from lower to higher, right? And so that means 180 degrees, doesn't it? All right. Now, we have a situation between the film and the substrate. How are we changing? Low to high, high to low? We're still going low to high, right? 1.3 is less than 1.52. So what's the phase change here going to be? 180. And so if, and I haven't gotten into path length difference yet, and we're going to get into it on Thursday. If we don't do anything to this phase relationship, if we leave it alone, then what will these two rays do? Will they constructively or destructively interfere? They will be constructive. Why will they be constructive? Because they are the same phase. They're 180 degrees different from the original, but 180 and 180 just means that they are matching each other, trough for trough and peak for peak. Because both rays have the same phase difference, they will be constructive. Okay, what's going on over here? By the way, 1 to 1.33 to 1, that's a soap bubble. So, what's the first bounce? We go from low to high. It's 180. Second bounce is high to low, so that's 0. And what are those two going to be? These will be destructive. Why are these two rays destructively interfering with each other? They are out of phase. They are not the same phase. 180 and 180 are the same. 0 and 0 are the same. 360 and 360 are the same. 272 and 272 are the same. Okay? Don't worry, you don't have to do the 272 degree one. But 180 and 0, that's exactly out of phase. 0 and 180. 180 and 360, those are all out of phase, perfectly out of phase relationships. And they will be destructive. So notice that we've had to apply what we know about how light interacts with material. Is it going to flip? Is it not going to flip? And then we have to figure out, okay, what is the natural relationship? If we change nothing, what is going on? Okay? And when we get together on Thursday, I'm going to give you the third step, which is where we get to change the thickness of the film to cause a path length difference to happen, which we can then alter what this second one is doing to get it to do what we want. I'll explain all of that and how soap bubbles work and how we clean up oil spills and why $20 bills have certain safety things on them that deal with thin films. I'll explain all of that on Thursday. Have a great rest of the day.